Welcome. I also made progress with PlayStation 3 video acceleration. Let's switch this on. So this is a petite bootloader where we select my, in the meantime, quite modified frame buffer kernel. In the last videos I showed you booting up and firmware upgrading the classic PS3 out of the basement. Thanks God all of this worked. However, initially Linux never had graphic acceleration. Sony for some reason did not really wanted this. Maybe they feared for a good reason that developers would DMA all their secrets out of the hypervisor, which I guess later happened eventually. Anyway, someone found some workaround to access the GPU back in a decade ago, 2007 or so. And this only worked for a short while until Sony changed the hypervisor to circumvent this tricky use of some FIFO mapping and ring buffer stuff. I had this running back in the day successfully and I was quite happy with this, because otherwise on Linux the GPU is doing nearly nothing, which is of course a little bit of a shame. This is some NVidia RSX, it's some NV4647 or so, so some desktop class CPU from a little bit over a decade ago. It's actually, I guess, probably not that bad. It's a little bit of a pity that you have there some hardware, and to be honest, not only does this make a great machine for tinkering and do-it-yourself use, it's also, now that so much is reverse engineered, it's even today a great machine for a nice do-it-yourself development, especially on the Linux side, especially if we would have more of the GPU working again. Back in the day, 10 years ago, 2007, I had this running with an X driver that had normal 2D blending and even X video acceleration running. It is also especially a shame because not only is the cell PowerPC CPU not that fast with some 3.2 gigahertz and hyperthreading. However, the 3.2 gigahertz, it's a little bit of a Pentium 4 fast clock, not really that fast for real workload kind of CPU. And if we waste so many CPU cycles on graphic, it's actually quite some performance lost. Also, the CPU doesn't have so much RAM. It's only 256 megabyte and another 256 for the NVidia RSX. So if we do not make good use of this additional video, then it's also quite a bit of a waste. For this reason, there is already a kernel driver that allows using the video RAM as quite fast swap device. That is certainly not the very best use of it. Also, I realized what nobody ever said is the normal frame buffer of Linux is actually allocating by default 9 megabyte of system memory as shadow frame buffer, which it always did even with hardware accelerated modifications. And I guess in the long term, if I would use this longer as a kind of nice alternative workstation or thin client or something like this, I would probably even modify this away and let the frame buffer only use video memory. The reason they did this probably is because reads from the video memory are much slower. To hide the slow reads, they implemented it like this, but when we have GPU-based splitting and blending working, we don't need this. Long story short, I now face a problem that hacking this to work a little bit required way more research, development and testing than I anticipated, and it is really too much to replicate now in this video. For the future, the question is if you, the audience, wants to see me live analyzing this kind of stuff, even if it leads to 20 minutes long videos that do not show so much progress, because the first days I made not much progress. Everything was crashing quickly. So what I show you today is basically the equivalent work of kind of 3 nights of analysis and hacking. And the question is also, how much do you want to see? Because the question is how many people will be able to follow these details. I'll now log into the cell with SSH for the simple reason that I can show you the screen recording, which is much sharper. I guess you will enjoy this much more than the far away text here from the small terminal. So what I did in the frame buffer, this is already with some patches from 10 years ago that change it slightly to already use features that are only available when we are running in GameOS, so that we have more permissions and can access more from the GPU. Additionally, on top of this, I had to make some more changes that are quite technical. The question is how much can I go into details on these videos. The long story short is that I also replicated here some additional IO-CTLs, some IO controls, to get some information to a user space. It's a little bit hacky. We don't want to have this in the long term, but I just wanted to have something working as proof of concept, it is usually better to have something working and then later refactor it into nicely secure and modular components, because this already took like 3 days. And if we spend weeks writing all the architecture, at the end it may not even work. I prefer to have something working first and then refactoring it into secure things. So I replicated here some IOCTLs. This one. This is from the decade-old modifications for this accelerated X driver. And I basically provide the same API. This only returns the size of the ReRAM, the FIFO, and some I/O control pointers. The original patch did some more modifications that I did not replicate because they were not used. That's probably more like debugging, that they wired out even more to user space applications. Then this also adds somewhere here. This is also a new I/O control for a new device that we create for testing that allows memory mapping, the DDR RAM from the GPU, and this command FIFO and some FIFO control registers. As I said, the original code return here more, but this is unused and I did not want it to replicate more than necessary. I had to change some small pieces here and there that I will have to later factor out when I create a proper patch of this. This is just a basic overview. And then I have here 2 versions of this old Xorg video PS3 driver that I unfortunately can't find in the internet. This is why it was really lucky that I had backups of this. Actually, initially I wanted to run this unmodified, but this only crashed. I had to also modify this a little bit. Actually, some areas I'm still not sure why some areas worked. They looked buggy to me. I have no idea how they could work. Maybe they only worked accidentally with the old hacked setup. And nonetheless, it was also good that I had an old version because I still could not get the slightly newer version working. The slightly newer version has, as you see, it also has Xvideo and slightly more full feature to deceleration. The older version does not have Xvideo and is way more compact. Initially I spent a lot of time hacking on this newer driver. Obviously I wanted not only more features, I also wanted Xvideo. But as I still could not get this to work, as you can imagine, tinkering with this GPU and memory mapping, memory regions and accessing graphic chip, I/O control registers and ring buffer and command buffer and things like this. Things can crash rather quickly. So actually debugging this, especially without knowing all the hardware details that are only reverse engineered, takes a lot of time. And obviously it took even longer time for those people who initially reverse engineered it, which is why I personally find it a little bit sad that so much of this is lost in the internet right now, as nobody took care of this for 10 years. But I'm really motivated to preserve this history and allow future, as there are millions of consoles out that potentially someone would want to run Linux on. I really think there is some value to have this working. So while working on this, as the X driver was more crashing than not, obviously the more I hacked and modified on it, the more it worked. But at the end it still wasn't working. I started to write small example programs to test my frame buffer modifications. Obviously, often when something crashed, I even had to reboot. So this kind of work is quite time consuming. Edit, compile, test, crash, reboot, edit, compile, test, crash, reboot. As you can imagine, that takes quite some time with all the research and debugging in between. All the reboots are a little bit annoying. Eventually I started to write test programs, this RSX test. So these are some additional devices that allow memory mapping, the video RAM, the FIFO command ring and the FIFO control registers. Just like the decade-old driver did, just forward ported and made to work again. And this code is a little bit like the X driver from back in the day. Opening the devices here, I cut and pasted code here together. Memory map here open and memory map the VRAM and FIFO control command ring. Some hexdump function, here's the main function. This first small test only opens this and hexdumps this files for me to check if we really memory map what we want to. Because initially even this did not work for all devices and ring buffers. As this is interfacing with the kernel, I had to write the kernel functions. It's not so easy to get all the kernel memory mapping, and there's physical address, virtual address. There is in the hypervisor apparently some logical partition, LPAR, hypervisor partition address, and so on. You need to allocate this from the hypervisor. You need to map this from physical to kernel virtual address space. You need to map this from the kernel into the user space address of the X server running in user space. So there's a lot of details that are easy to get wrong. Then the next test was, I also kept this task, so you could also put this in different functions of one test driver. When one thing was working, I copied it to the next. Next, I probably tested writing. This is basically the same program, just modified to write here into the control registers, hex dump them again to see if this works, and also this command ring FIFO. And only after I was sure this was working, I often also compared with the X driver actually. But as this often did not work yet, I wrote the next test, which is to patch a jump into this command buffer. This command buffer is what the GPU is executing. So I copied the code that was already in the kernel and the X driver and test getting the current FIFO command buffer pointer. That is an internal register of the graphic card. And at this current location of this command buffer, I patch in a jump to the start of the ring buffer just to make sure that all the mappings work and that actually writing something in the command buffer and triggering the command buffer for the graphic card to execute the next instruction from it actually also works. I show you this in such detail to demystify programming of kernel programming and also device driver programming. And if you do this step by step in simple programs, then you can learn a great deal and everyone could eventually get into this. Obviously, first it's easier to start learning with normal small programs, but later, as soon as you advance in programming, you can also eventually do kernel programming. It's not so much different from normal programs. Probably even this jump patching did not work at the first try. You see this address is not even 0. This address is the start of the FIFO address as seen by the graphic card. And this FIFO is mapped at this define that is used in the kernel and X driver. So this FIFO lives inside the graphic card at address hex D0000 and so on. So obviously you cannot jump to 0. If you want to jump to the beginning of the FIFO, you need to jump to the beginning of the FIFO physical address of the graphic card. Anyway, eventually after all this test and comparing with the X driver and rebooting and modifying the X driver, eventually I started to look at this old X driver, which was way more simple. And after a lot of analyzation, fixing and improving all these details along the way, of course it looks quite easy when I present you the small example programs. In reality, you probably sit hours staring at this even simple code examples and wondering why the graphic card hangs, why the kernel panic, why you get a graphic card exception from the hypervisor and things like this. Last night, finally, I got the first glimpse of hardware accelerated X driver running, which I can present you today. I hope it doesn't immediately crash on me. The other video was just the secure shell that is locked into the same machine. I also start the X server here from this shell. Then we see debug output. So what I still need to analyze, the startup takes quite a while. I'm not yet sure why. Apparently, I guess there is something wrong because I think this is not normal that we run so many, what was it even, kicking this DMA command buffer or something. I think it's either no operations or only jumps to the beginning of something. I have not yet analyzed why that happened, but you've seen there was plenty of stuff scrolling by and this is not normal and takes quite a while. But these are the things, even you see there is something working. So now my next steps are, why are this hundreds, thousands of no operation commands happening, probably due to some bug that I need to find. As you can probably see, there is graphic corruption. This is not yet 100% awesome. I hope it's seeable. These icons here are corrupted. This is already moving correctly, except when I stop, then there is some slight corruption happening. And you see when I move here things, there are a lot of commands scrolling by. And this is already huge progress. You probably may think, how can this strange guy be so happy about those graphic corruptions? These are 3 days of free time just for fun, working night shifts on this driver stuff. And after 3 nights debugging this, you are really happy to see any graphic at all and not a crash. It may even look up, so be warned that if we do too much, it may eventually crash. But this is already huge progress, and even stuff displays here correct, and even some high frequency updates are correct. There obviously still is something wrong as seen by these icons, for example, but even the mouse cursor moved here is, you see DMA operations. Actually, I realized this code never had hardware cursor, and I've seen Sony later added support for hardware cursor calls to the hypervisor for their game OS. So we could now even probably try to make use of this new hypervisor calls to add hardware cursor support later. But right now, this is drawn by DMA operations, as you can see, blitted from off-screen cursor pix maps by the regular 3D engine. Actually, I'm surprised that this is shown correct. Anyway, as you see, there is still a lot of work left, figuring out what strange stuff is going on startup, figuring out why this graphic corruptions of some transfers happening. And this will be again hours, if not nights, of debugging, which can be fun if you are into hardware debugging and tinkering. If you are interested in this, I have to share this code as soon as possible, not that it gets lost in the decaying internet again. If you want to contribute hacking on this, drop me a note. I will be totally happy about everyone who wants to help me getting this to work better. The original code had more 2D operations running and even NVidia acceleration. And theoretically, these are 3D operations. There is nothing stopping us from implementing 3D support for this NVidia RSX on the PS3 natively. I would suggest to start with small example programs, but it can be done. I will at least try to find enough time, maybe supported by YouTube videos. Time will show. Let me know in the comments below what you want to see and what not, what is too detailed and what should be more detailed. I invite you. There is a lot to learn if you want to get started in Linux. This driver is not big. This is quite small. There is quite a lot to reverse engineer. This is a quite normal, only slightly modified NVIDIA chip that you can copy and paste code and defines from the Mesa OpenGL 3D driver that exists in the regular open source Nuevo project. So before I get into debugging the more complex driver, I better want to understand this NVIDIA chip in detail and get the simple driver running, which is obviously way easier to debug, especially as it's running already. I find it usually much easier to debug something that is at least running a little bit than to debug something that's not yet running at all. That's it for today. I hope it was not too technical. Maybe in the future, as it's a little bit hard to replicate everything I debugged, I'm thinking in the future to potentially film more raw while I'm actually doing it. I hope that could produce more interesting content with the actually debugging and fiddling that I'm doing, and even save a little bit of my time because I don't have to sit here another time and work you through the source code changes I made. I hope that could be more interesting for you. It would be awesome if you could leave in the comments below what you think about this, and don't forget to subscribe for plenty of awesome tech videos to come.